So this one says, how much heat is needed to convert 50 grams of ice at minus 20 to steam up to 120? So the way that you do these is you want to first make a curve to illustrate where you have to go. So again, we have temp as a function of heat added. And it goes up, melts, up, boils, and then up some more. So what might be this temperature at the bottom here? So is it 0 or is it minus 20? Yeah, this is going to be minus 20. This temperature right here, what's that going to be? For water, right, for water it's going to be 0. That's the temperature at which it melts or starts to melt. And then what about this temperature right here for water? This kind of, I'm asking you for some common knowledge, but yes, it's 100, right? So this would be 100. And what about the very top there? That's going to be 120. Okay, so now that we kind of know what's going on, I think it helps to see the curve. And now we can calculate the heat change with every step. So for this step, Q is going to be equal to what? MC delta T. Okay, for this part, Q is equal to M delta H fusion. For this part, Q is equal to M catechid. For this phase change, Q is equal to M delta H vap, or vape. I should say vape, that's like what's going on right now in the streets. People make a big fuss out of vaping, I don't know what it is. All right. And then you got Q at the very top there. Actually, I'm sorry. It's this whole Q is equal to M catechid. So let's do the calc. So what's the mass here of the water? 50 grams. So we get 50.0 grams. And what is the specific heat of ice? Because right now we're dealing with the ice. Yeah, 2.22 joules, right? 2.22 joules per gram per degree C. And what is my delta T? Yeah, so my final temp is going to be 0. My initial temp was minus 20. So this delta T ends up becoming positive. All right, so this part comes out to be 2,220 joules. For the phase change of melting, I still have 50 grams of water. What number do I use for delta H fusion? 335. And this is in just simply joules per gram. All right, so this comes out to be 16,750. out again, we're doing 50 grams. So notice how the mass of water isn't changing. Right? It's 50 grams of water in the gas phase is the same as 50 waters of gas in the liquid phase, which is the same as 50 waters of water in the solid phase. Specific heat of water in the liquid phase now is going to be, what is it, 4.18? And delta T is going to be what? Yeah, 100 minus 0.0. Alright, so that's going to come out to be 20,900. Alright, for the boiling phase change here, again 50 grams. Delta H vape is 2.01. No wait, 2260. Okay. All right, that's going to give me 113,000 joules. All right, and then for the gas being heated up further, all right, that's going to be, again, 50 grams. Specific heat of water vapor, 2.01. And then what's my delta T? All right, 120 minus 100. So notice how the delta T is in place only for the rising parts. Right, but I don't have delta T for the phase changes, because again, for a phase change, temperature stays constant. So this will be 2010. So you add these all up now to get the overall heat exchange for the whole process, right? And you would get 155,000 joules, positive 155. So this is the heat you had to put in to heat water from minus 20 up to 120. I think that looks semi-legible, hopefully. Okay, so just making sense of this. If you look at the steps, which step required the most energy and why? Okay. Which step required the most energy? Clearly 113,000 took a lot, right? It took a lot of energy to boil the water. Why is that? Hydrogen bonding, right? When you heat up water, you have to break those hydrogen bonds apart, literally get them apart, okay? So we're relating this back to IMFs, right? Maybe fascinating, but really real-world experience here. Let me ask you a question. If I were to go cool the water back down to minus 20, what would the answer be here? If I went back from 120 down to minus 20, how would it change this number? It would just become negative, right? Because you got to take that energy out now. You got to take that heat out to cool the water back down. So the first law plays a factor, right? Like the first law comes back into play there. Energy is conserved if you go one direction or the other, the same energy. Getting to this 113,000, if you condensate the water back from 120 down to 100, and if you take that heat of the phase change, if you cool 50 grams of gaseous water back into liquid again, you're having to take 113,000 joules back out again. So in other words, heat has to be taken out from the system and it goes back out to the surroundings again. How many of you have ever been burnt by hot water? How many of you have ever been burnt by steam water? Which hurts worse? Steam. Why does steam burn worse? Because of this phase change here. So this 113,000 ends up going back out into the surroundings. The surroundings includes your hand or your arm. Okay, and that's why steam burns hurt so much worse than say if the water was already hot and it was just hot and it cooled down. But now you get this phase change from the steam, which really hurts. Okay, so in your everyday life, avoid the steam because it's going to burn you a lot worse because the phase change is going into your skin now. Our body temperature, normal body temperature is around 37 degrees Celsius. So if we get burnt by steam water, we go through this phase change and then back down to 37. Versus if you're just being burned by direct hot water at 100, it's just from 100 down to 37 without the phase change. So steam burns hurt a lot worse because of that heat of vaporization, right? It just hurts a lot worse because of that. In my days as a parent, I can tell you right now, we used to use these bottle sanitizers. You ever heard of the baby sanitizer? It's a plastic container, it's got a rack, and you put the bottles upside down in it. In the bottom is a pool of liquid water. You put the bottles in there, the nipples, the caps, everything, okay? Put them in the microwave for 3.5 minutes, and you open it up again, you pull it out of the microwave, and it's all steamed up in there. Okay, why would you ever want to do that? Well, because when you create all this steam and it recondenses, okay, it burns the baby bottles, the nipples, the caps, everything, and it invariably would kill more microbes that way because you're putting more energy into those bacteria and get rid of them, right? Or any virions that might still be on there. Okay, so that's another everyday application of phase change from the trenches of parenting. But yeah, everyday life, right? So anyway, so phase change is kind of cool, and there's an application showing it. But why do steam burns hurt worse? Because of the heat of vaporization part, right? The phase change takes up the most energy. All right, so it looks like we'll have to stop here, but we'll finish up a lot tomorrow.